So, good afternoon, everyone. Myself is Dr. Ajit Kumar, and I am faculty in the Department of AC at Presidency University. So, we'll continue our lecture in the microcontroller and its application. So, in the last class, we were discussing about the addressing modes of 8051, and then we continued for push and pop instruction. Okay. Today, we'll discuss about the memory interfacing. Okay, memory interfacing with our microcontroller. So in general, before I start our 8051 microcontroller interfacing, I'll talk something that how your memory chip is actually connected with microcontroller. Fine. So we'll start with very less capacity memory chip so that you can understand the concept properly here. Fine. So suppose, let's say, very simple concept. Okay. Let us assume that this is your microprocessor, okay, or microcontroller, whatever you use. So at this moment, let us try to understand from microprocessor concept only. Okay, now this microprocessor is, let's say, interfaced with memory chip. Now assume that there are only four locations. Okay, in each location, 8-bit data can be stored. Okay, we are assuming very small memory chip capacity. Small memory chip capacity. Okay, so in which I'm assuming that there are four locations. Four locations. In each location, okay, each location 8-bit data can be stored. 8-bit data can be stored. Can be stored. Fine. So let us assume this. So if there are four locations, okay, four locations, and I know that the microprocessor understand only machine language that is composed of zeros and ones, okay, zeros and ones. As such, now here what is happening? If suppose that I have stored some data in this memory chip, okay, in data or let's say program, whatever you use, data or code, fine. Now, who is going to execute the data or the program? It is the processor who is going to execute this one. Fine. So that's why they are connected. Okay, this microprocessor is connected with the memory chip with some set of bus, which is called address bus. Okay, data bus. So like this 1, 2, 3, 4, 5, 6, 7, 8. I'm giving 8 lines here. So 1, 2, 3, 4, 5, 6, okay, 7 and 8. This is your data bus. And then there is a third bus which is called control bus. So what is happening? These buses are used to connect, used for the communication purpose between this memory chip, okay, and microprocessor. Okay, not only this much, there are further more things that we will discuss at this moment. Let us try to understand that there are four locations, and in each location, 8-bit data can be stored. Okay, so 8-bit data could be anything, your program code or instruction code, or it could be a simple construct number. Fine. Now, try to understand that this locations, okay, suppose that just like example is there that let's say that postman is there, okay, that postman is supposed to come to your house and deliver letter or receive letter. So first of all, what is required is that postman should be knowing about your house location, house address, otherwise he won't be able to reach you. Similarly, when you store something, okay, whenever you store any data here, okay, 8-bit data, here also 8-bit data, 8-bit data. So this 8-bit data can be actually accessed by the processor, okay, only if their locations are known or their you can say addresses are known. For this purpose, we assign, okay, the designer assign the address to each locations here. So I know that there are one location, two location, three location, four location. If there are four locations, I can assign addresses using how many bits? It could be 2 bits, 00011011. Using the combination of these 2 bits, okay, I got here four locations. Okay, try to understand this one. So I'll give addresses here, something like this. Okay, let us start from here. The lowest address is 00, then 01, then 10, then 11. These are the addresses here. Similarly, if I would have a larger memory chip capacity, something like this, okay, in that memory chip, so let's assume that 8 locations are there. One, 2, 3, 4, then 5, 1, 2, 3, 4, 5, then 6, and then 8. Now here I have 8 locations. Okay, in this case I have 8 locations. So how many bits will be required here to assign the addresses? I can use three. I can use a combination of 3 bits. Okay, that is, if I take the first location as this one, I can give this address. Then 001, then 010, then 011, then 100, then 101, then 110, 111. Okay, like this I can assign the addresses. In the decimal, you can say that this is decimal 0, this is decimal 1, this is decimal 2, decimal 3, decimal 4, decimal 5, decimal 6, and decimal 7. So in the decimal form, this is the address number, and this is in the, you can say, hexadecimal form. Not hexadecimal, right now it is using 3 bits, so I'll say binary number. Fine. What is the point is here? Here I was here I was using 8 locations. Okay, so I used 2 bits. Okay, that is how I got. Sorry, here I was using 4 locations, so I have used 2 bits. So that is 2 power 2 bits. Okay, is equals to 4 locations. Try to understand this formula. Similarly, here also I am using, no, not here, here, 8 locations, so I am using 3 bits. How I got this one? 2 power 3 bits. I am writing here bits just for the sake of understanding, and otherwise it is simply 2 power 3. So I got 8 locations. So in general, there is a formula. Okay, what is that formula? That suppose, so what is that formula? Number of location is equals to 2 power n. Okay, where n is the number of bits. Okay, this is the formula. Now, if each location, if each location can store 8 bit, okay, can store 8 bits, that is 1 byte. Okay, so let us say the previous first case. What is the memory chip capacity for this one? For this case, the memory chip capacity means the number of total bits that can be stored. So here I can store 8 bit, 8 bit, 8 bit, 8 bit. So that is 32 bits. Now this 32 bit in the terms of byte can be written as, because I know 8 bit means 1 byte. So that is here 1 byte, 1 byte, 1 byte, 1 byte. So it is 4 bytes, 4 bytes. So in general, what is the formula? How, I mean, similarly here also, try to understand. Here also, 1 byte data can be stored, 1 byte, okay, so 1 byte, here also 1 byte, here also 1 byte, okay, 1 byte, 1 byte. So total capacity is 4 into, sorry, number of location, number of location into 1 byte, because 1 byte data can be stored here. Number of location is 8 into 1 byte is 8, that is 8 bytes. This is the memory chip capacity. So in each location 1 byte data can be stored. Okay, so if there are n number of bits, okay, for n number of bits, I can have 2 power n locations, and in each location 1 byte data can be stored. So the capacity is 2 power n bytes. This is the memory chip capacity. Uh, you might ask, sir, whether it is necessary that each location can store 1 byte data. Mostly, okay, mostly almost all the microprocessor microcontroller, we will see that 8-bit data is, or you can say 8 byte, 1 byte of data is actually stored. Okay, so that is why I'm saying that 1 byte data is stored. So if there are 2 power n number of locations, then I can have here 2 power n bytes storage. Okay, now recall in 8051 microcontroller. Okay, come to our 8051 microcontroller. Here, also one thing that I missed to explain is, see, suppose now this is, I said that this is address bus. Address bus is always unidirectional. The address always goes from microprocessor, okay, to the microcontroller. So microprocessor to the memory chip. Whereas the data bus is bidirectional. Bidirectional means the data may go this way from memory to the processor, or the data may go from processor to the memory chip. Okay, so there is bidirectional, and this control bus is unidirectional processor from processor to the memory chip. Now, what is there is, uh, let's say how it actually works. Let's say that here 8-bit data is stored. Okay, suppose here this 8-bit data is stored. Okay, let us assume that this 8-bit is something like this: 0, 1, 0, 1, that is 5, and 0, 0, 1, 0, that is 2. Okay, so this is the 8-bit data which is stored here, and let's say the processor wants to execute fetch this data. So how it is going to do? First of all, in microprocessor we have a register which is called PC. Okay, not necessary PC. It depends upon. I mean, we have for the different processor we have different registers for storing the address. For here, I'm assuming that there is program counter register. The purpose of this PC register is used, I mean, to store the address of the instruction address of the instruction, or you can say address of the data from where the data or instruction has to be fetched. Right, right now I'm assuming that this is a constant data. So this constant data is residing in which address? 11. So this 11 address will be actually stored by the PC register. Okay, the PC, as the name suggests, it keeps on counting the next address from where the data has to be fetched. So this PC, which is actually storing the address, will be loaded on this data bus. So there are two electrical buses here. Each electrical wire will carry one bit. So this binary one, which is the address, will be loaded on the address bus. It will be received by the, it will be loaded by the processor into the address bus. It will be brought to the memory chip. Now the memory chip is actually not knowing that what the processor is going to do with the data which is in this address. Okay, the processor can do two things: either it can replace this data with new data, or it can read this data, means fetch the data. Okay, so let us assume that at this moment the processor is going to fetch the data. So in that case there is another bus which is called control bus. Okay, so this control bus, there is a control unit inside the microprocessor. So this control unit is actually used to generate the control signal. Okay, this is used to generate the control signal. Control signals like memory read, memory read, memory write, then IO read, IO write. These are the four control signals which are generated by the control unit of microprocessor. Okay. So all these signals are either binary zero or binary one. Okay, they are, though they are, I'm saying they are signal, but the signal doesn't mean that they are any electromagnetic signal, sinusoidal signal. Okay, here the signal means they are actually binary one or binary zero. Okay, so for example, this memory read in the short, it is designated like MEM R bar. So it means it is zero. Okay, the signal is zero. Okay, so in that case, this is zero. Similarly, memory write is designated by like this MEMW. Okay, like this. And if it is active high, then it might be binary one. So this could be a binary one. Like this, the different signals are generated in terms of zeros and ones. So what is happening in the first here in the step one, the address was loaded and sent to the micro this memory chip. In step two, this control bus, I mean control unit will generate a control signal. At this moment, you see here there are two things: memory read, memory write, and IO read and IO write. So if you recall, I told you that this processor can can communicate with two devices. One is input device like keyboard or mouse, and then there is another device like output device. Okay, output device like monitor. So we know that when you press something in the keyboard, okay, let's say alphabet A you have pressed, then a signal is sent. Okay, that is called read. Okay, in that case it is called read, and then microprocessor will receive the signal after read operation. Okay, so this time the processor is going to read the data from the input device. So input device, okay, so I'll say that in that case IO read signal is okay generated. See, it is actually done like this. There is a control bus. This control bus will carry IO read signal. Okay, then this data will be brought inside the microprocessor through the data bus. Okay. Similarly, here this microprocessor, if this wants to display that the signal, then there will be another signal which is going from microprocessor to the output device is called IO write. Okay. So this IO write, it is going to indicate this out monitor that it is going to write something, and then on the data bus it is going to send that signal, and the monitor will display the the signal that was received from the keyboard data. Okay, so here IO read and IO write signal is generated. Why? Because it is communicating with IO devices. However, and in this case, it is communicating with this memory chip. So memory read and memory write signal will be used here. Okay, so memory read and memory write signal will be used here. So what I said in the step one, the address is loaded on the address bus. Okay. In step two, the control bus will carry the control signal because it is communicating with the memory chip. So memory read, MEMR, memory read will be generated by the control unit, and because it is active low, it's so a zero is transmitted. Now try to understand what is active low, active high signal. Okay. See, in the microcontroller, sorry, in the digital these electronics, you people might have studied about this. You are already aware of this one. What is that? In the like A B bar. So here see, this A is active when it is binary one. Okay, this B bar is active when B is zero. Because if B is zero, then B will be B. Then if B is zero, then B bar will be one. Okay, so that is why I'm saying that it is active for low signal. So it is active for low, okay, and this is active for high. Similarly, if I am saying that it is MEMR, memory read, then it is active for, because a bar is there, so I'll say that it is active for low. So I'll say active low signal. Okay. Likewise, if there is another signal, let's say PSEN, which I discussed today, PSEN, there is no bar, so it is active high signal. So in that case, no, I was saying that how it is working. Okay, let me draw a separate figure. That figure has not very exactly. So let's say this is your microprocessor. Microprocessor. Let's say this is your memory chip, and I'm assuming that there are four locations. In each location, 8-bit data is there. Then we have this that address bus, which size is 2-bit. Okay, this address bus size is 2-bit. I'll trail the significance of this one. And then I'm assuming that there is data bus which is 8-bit. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is the data bus. Okay. So this is data bus and this is 8-bit. And then we have a control bus which is 1-bit. Now, please try to understand why this address bus size is 2-bit, because I said that only 2 bits will be required to assign the addresses to the different locations. Okay, so I'm assuming that some data is there. Okay, that data, okay, it could be any data like 1010, okay, 1011, something like this. 8-bit data is there. So inside the microprocessor, we have a register PC which will be always pointing to the address from where the data has to be brought or from where the data has to be written. Okay, from where read and write operation has to be done. So that PC address is loaded on this 2-bit address bus. Okay, so the 2-bit address bus means two electrical wires. Each electrical wire will carry 1 bit each. Fine. So here 1 1, which is the address. This address, okay, is loaded on the address bus. That is why its name is address bus. Okay. In the second step, this was step one. Step 1. Then in the step 2, the control bus comes. The control bus will carry the control signal which is generated by the control unit. Control unit is inside the microprocessor. Okay, so this control unit will generate a binary zero, that is for memory read. So this memory read is a control signal which is generated by the control unit, which is basically active low. So a zero is loaded on the control bus, and this zero will be sent to this memory chip. So after step two, the processor will know that from this address, which was sent by the microprocessor in step one, okay, in step one, so from this control signal, which was received by the memory chip in step 2, the processor will, sorry, the memory chip will know that this data, okay, this data is actually required to be read by microprocessor. So this data will be loaded on this data bus in step 3. Okay, so in step 3, this data 1010, okay, that is, as I said, that there are 8 bits. So 8-bit means 8 electrical wires. So 1010, okay, then similarly 1011, this 8-bit data will be loaded on the 8 electrical wires, that is your data bus, okay, which will carry the data to the microprocessor. So once this data is received here, 1011, okay, 1010, something like that. So this data will be brought inside the processor, which is called fetching. Okay. So this is how the communication actually occurs. Let's say that the processor wanted to write something in this location. So step one is same. It will send the address from the PC on the address bus. Step two is different. In the step two, it is going to load on this control bus memory write signal. Okay. This is how it is differentiated. So in step two, memory write signal will be sent to the memory chip. The memory chip will understand that microprocessor wants to not read something but write something. Okay, so in step three, the microprocessor will load the data on this, okay, data bus, and that data bus will carry the data to the memory chip, and that data will be stored here. Okay, stored here. So storing is called write. Okay, and taking the data is called read. So this is how the read and write operation is defined. Now, similarly, when I have taken the case of this one where I was assuming that this microprocessor is connected with, let's say, eight a memory chip having eight locations: one, two, three, 4, 5, 6, 8. And I know that we can assign 3 bits to assign address to 8 different locations. So 001, 011, then this is 012, so 2 means 10. Then 3, then 4, then 5, then 6, then 7. So here 3 bits are there, 3 bits for address. Okay, so can you guess what could be the size of your address bus here? What could be the size of address bus here? In the previous case, it was in the previous case the size of address bus was 2 bit because there were two locations. This time the size of address bus will be 3 bit because there are three locations. Oh, sorry, 3 bits for the address. Okay, so this time address bus is 3 bit. Data bus will remain as 8 bit because I'm assuming that 8 locations are there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 like this. So this is your data bus, which is bidirectional. This is address bus, okay, which is unidirectional, and there is a control bus which is 1 bit always, and this is also unidirectional. Okay, so here I had 3 bits. Okay, 3 bits, and here I was having 8 locations. In each location, 1 byte data is there, so I'll say 8 byte was the memory chip capacity. Fine. Now come to our 8051 microcontroller. These were the cases where I was dealing with a smaller memory chip capacity. Okay. However, in our microcontroller 8051, you will see that you just recall this fact 8051 that our PC register is 16-bit register. So you know 16-bit register means the PC can store starting value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the starting value. So next value will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1. So next value will be 0, 0, 1, 0, 0, all the zeros, then 1, 0. Okay, so like this, it is 0 decimal, it is 1 decimal, it is 2 decimal. So like this, we can store here up to the maximum value that can be loaded on this one is 1, 1, 1, 3, 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is, that is, this is 0, this is, then this is like 65,535. So this is in the decimal, the equivalent decimal. Now let us try to come to this one that how you might ask how we have assigned all the ones to the last address and how we have assigned all the zeros to the last address. It is very important to understand. If you see the previous cases, when I was considering the 4 locations, okay, that is 2 bit, then you see the last address was 2 ones and the first address was 2 zeros. Similarly, if I am considering 3 bits, then the first address was 3 zeros, the last address was 3 ones. Okay, like this, if you observe here, okay, in 8051 microcontroller, since PC actually stores the address and this address is 16-bit, so I can say that the first address will be 16 zeros. Okay, similarly, the last address will be 16 binary ones. Okay, so in general, I can say that here our 8051 microcontroller can be interfaced with a memory chip, okay, whose starting address can be now. I'm not going to write 16 zeros. Okay, what I'll do, I'll write it in the hexadecimal form. So you know that in hexadecimal form, this 0 can be written as single 0. Then the next 4 0 can be written as this 0. Similarly, the next 4 zeros, single 0. Then the next 4 zeros, 0. So in general, I can say in hexadecimal, I'll write this as 000H. Okay. Similarly, the next address is 0 0 0 and 1. So I'll write this as 0 0 0 1. From where 1 came? From this 4 bit. Okay, the lowest significant 4 bit. Similarly, the next address could be 0 0 0 2H. So like this, I can assign the addresses. Okay, so like this, it keeps on growing, and the last address is all the 16F. So sorry, 16 ones. So this 4 ones, you know, it can be written as F in the hexadecimal. This 4 1 can be written as F in the hexadecimal, F, and 1 2 3 4. So this F. So 4 4 4 4 16. So these two are unnecessary. So I will write here as F F F H. This is the last address, and this is the first address. Okay. Now, because our address is of 16 bit, so I need here address bus size 16 bit. Means there will be 16 electrical wires for address bus. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is your address bus, and this is unidirectional. Okay, so this is your address bus. Similarly, I'm assuming not. I mean, we can store here 8 bit in each location. So 1 2 3 4. So 1 2 3 4. Then 5 6 8. Okay, 1 2 3 4 5 6 7 8. 8 bit. Okay, 8 bit. 8 bits in each location. So I will again need the data bus which is of 8 bit. 1 2 3 4 5 6 7 8. Okay, 1 2 3 4 5 6 7 8. So it is bidirectional connected like this. So these are 8 electrical wires. So this is your data bus. Similarly, we have control bus which is unidirectional and is always 1 bit in the size. Fine. So this is the case of 8051. Now, can you guess what is the memory chip capacity for this case? What is the memory chip capacity? Oh, just see here. How many total bits we are using? 20 bits. So how many locations can be there? 2 power 20 location. 2 power 20 location is equivalent to 65,536. Okay, in the decimal. These many locations are there. In each location, I can store, okay, these many locations are there. In one location, in one location, I can store 8 bits, that is 1 byte. So in this 65,000 location, I can store 65,536 bytes. This is your memory chip capacity. Now, because I have used here decimal number system, so this is coming like this. But however, this is actually 64 kilobytes. Now, why this came? Try to understand this. Okay, this is the capacity. So if you recall in our binary number system, if I have 10 bits, okay, no, not 10 bits. Let's say 1000. Okay, that is, you know, we are using binary number system. Okay, that is 0 and 1. Okay, Now recall 2 power 10 is 1024 bits. It is not 1000 bits. Okay, that is why this difference comes. Okay, here one 1 kilo bits is equals to 1024 uh, 1024 bits. Okay, so 1k 1 kilo means not 1000. Okay, not 1000, but it is 1024. Okay, that is why this difference comes. Okay, so and what is 1024? It is 1k. Okay, and what is 1k? 1k is always equals to 2 power 10. Okay, so if you keep it, and that is if you increase to power 20, then this becomes 64k. Okay, okay, and since each location can store 1 byte, so it is 64k byte. Fine. That is why I'm getting 64 kilobytes of memory chip capacity that can be interfaced with our 8051 microcontroller. Okay, so now let us try to see one basic thing. Okay, uh, what is that concept is, since we started our discussion with memory chip interfacing, so we should understand that there is something which is called chip selection. Okay, I will start again with very small discussion. Okay, suppose that this is your microprocessor. So let's say we have here mm, two memory chip. This is first memory chip. This is second memory chip. Now, okay, I'm assuming that this one memory chip capacity is not enough, so we are connecting second memory chip also. Okay, so that our microprocessor do not suffer from shortage of memory chip. So I'm connecting two memory chip. Okay, now here what is happening that these two memory chips are having common connection. Okay, are having meaning for each one of these we have common address bus and data bus. We do not have separate address bus, data bus. Okay, so if I'm saying that this is address bus, then the same address bus is also for this one. Okay, and if I'm saying that we have a data bus, okay, let us take another one. If I'm saying that this is data bus, then the same data bus is also connected here. If I'm having control bus, then the same control bus is for this one and for this also. This is control bus, this is data bus, and this is address bus. Now, what's the case is the let's say that here we have four location in each memory chip. Simple case. So if there are four locations in each, so I know that 2 bit will be required to assign the address. So for this address will be 00, for this 01, I mean 0001 1011. Similarly, for this also I'll have to assign 2 bits to addresses, that is 00, 01, 11, sorry 10, 11. Now can you see that both memory chip is having common address, I mean the same address names, that is 0000. First location is 00, second is 01, same in all both memory chip we have same addresses. Now for this purpose, no, let's say something, let's assume that here some data is stored, 8-bit data is stored. Okay, let's say 8-bit data is stored, 1 2 3 4 5 6 1 8. Similarly, let's say same address I'm taking 1 2 3 4 5 6 and 8. So let us say 0 1 0 1 0 1 0 1 is stored, and here let's say 1 1 1 1 1 1 in all the 8-bit location 1 is stored. Now what is happening? Suppose that this data has to be, okay, read by the microprocessor. Okay, this has to be read by the microprocessor, which is an address 10. Fine. So what is the first step? We know that there is a register which is PC. PC is always pointing to the address from where the data or instruction has to be fetched. So at this moment, this 10 will be loaded on this address bus. So here it is 2 bit, okay, that are not showing. So that is one binary and 0 is loaded. And then now the question is, to which memory chip? This memory chip the address will come, or this memory chip the address will come? Okay, this is the question. Okay, so it is not like this. Okay, there is something which is called chip selection, because see, the microprocessor can let's say this is first, already said, first chip, second chip. So the microprocessor can either be you access the data of your memory chip 1, or it can access the data of memory chip 2. Okay, at the same time it is not going to access the data of both memory chip. Fine. So there is something which is called chip select, or you can say chip selection. Okay, chip selection. Now this chip selection is a pin, okay, which is available in all the memory chips, here also and here also. And this is active low signal. Active low means it is active only when it is 0. Okay, so this is active low. So I'll place a bar here, here also bar, to show that both are active low signal. Okay, now what is happening? Since I'm saying that the data has to be read from the memory chip 1. Okay, so for that purpose, the first memory chip should be selected. Okay, for that purpose, first memory chip should be selected. Okay, so what is happening? There is uh, there is another signal, okay, which will be transmitted from the microprocessor to this CS pin, okay, and to this CS pin also. Now, what is happening? Uh, if if so, what is happening? A binary is, suppose that this memory chip, first memory chip has to be accessed by the processor. So at that time, the microprocessor should send a binary 0. If why binary 0? Because CS is active low. So after receiving a 0 from the CS pin, the memory chip will know that the processor wants to read something or write something from my memory chip. Okay, and not this one. Okay, so in that case, the data will be loaded on this data. The address of this data bus will be loaded on the data bus, and it will be provided to the memory chip. Okay. However, if suppose that this memory chip has to be selected, so in that case, this electrical wire is, okay, from the same electrical wire. There is another connection which will go something like this. So recall, if a 0 is sent from this microprocessor, then this first memory chip will receive 0. But because of this NOT gate, this 0 will be inverted and a binary 1 will be received by this memory chip. So if this memory chip has received binary chip, means it is not selected. Why? Because it is not selected because CS pin is not enabled. Okay. However, this is selected. This will be selected. Okay, this will be selected because because CS pin is enabled. And who enabled it? Microprocessor. Okay, this is how it is. This kind of connection is done. Okay. And this NOT gate. Okay, this NOT gate is actually called address decoder. I'll show you that address decoder can be designed in many ways. Okay, this was a simple case. Okay, so in this case, now what is happening? This one. Okay, this chip will be enabled. This chip will be enabled if it receive binary one. Okay, so in that case, okay, we add another bit here, and this because this memory chip will be enabled when this is having zero. Okay, that is we add here 0 0 0 0 0, and we add here 1 1 1 1. Now see here, it is 0, it is 1, it is 2, it is 3. Okay, similarly it is 4, it is 5, it is 6, it is 7. Fine. So what is happening? See, I will redraw this diagram so that you understand it. This is microprocessor. This is our first memory chip, chip 1. This is our second memory chip, chip 2. Okay. Now here we have three buses. I'll assign their name as A0, A1, A2. Okay. So A0, A1, A2, like this. Fine. Similarly, so I'll assign this A0, A1. Similarly, the same bus is coming here. Okay. So which I'll show something like this. Uh, A0, and this bus, same bus is, as I said, the same electrical wire is used to connect the both one. So it is A1. Now this A2 bus is okay directly connected to this one, but it is not directly connected. Okay, one more thing. This A2 bus is connected to CS input pin. Okay, and this A2 bus is also connected to this, not as it is, but a NOT gate is connected. This this one went directly. Okay, so this I'm showing in blue, and this one also in the red. The same bus is now passed through a NOT gate, and this is connected to CSP. Now see here what is happening. We have assigned here 8 locations. One, two, three, four. So I've assigned here 8 locations. 1 2 3 4 5 6 7 8, like this. Okay, the first one I will giving orders. Oh, because we have taken only 4 locations. Okay, so not 8 locations. So I'll take only 4 locations here. Like this. 1 location, two, and then 4 locations. Similarly for this one also, one, two, and 4 locations. Okay. Now see here, using this A2, A1, A0. Okay, I can assign total. I can have total here 8 combinations because this is our bus. No bus. This is our bus. So I can have 8 combinations. What is that? 0 0 0, 0 0 1, 0 1 0. So 0 1 2, then 3. Okay, like this. 4, 5, 6, 7. Now see here. Let us divide this into two parts. From here to here. Okay. This one will be used for memory chip 1, and this one will be used for memory chip 2. Okay, now see here, if I have given these addresses, so here this addresses will be written as it is 000001 010 and for this one that is 4 1005 6 7. Okay, where this is a naught, this is a1, this is a2. Where this is a naught bit, this is a1, and this is a2 bit. Okay, now see here in the a2 bit, see here the a2 bit is 1. Okay, similarly see the a2 bit of this one, it is 0. Now this A2 bit is connected, this A2 bit is connected to this CSP. So if a 0 is sent and received by this, then this chip will be selected. Okay. So if A2 is 0, then chip 1 is selected. And similar, now this, suppose at the same time, now this 0 is coming here. So this will become binary one. So this will not be selected because until unless a 0 is not received, this chip second chip will not be enabled. Okay, for both chip selections, 0 should be received. So okay, similarly, if A2 is 1, then chip 2 is selected. Okay, and at that time, chip 1 will not be selected. Okay, so suppose that I'm taking this one. Okay, this. So let's say this one, this A2 is sending binary 1. So binary 1 is received here. So this is not selected because it is not enabled. Now because of this NOT gate, the same one is coming as input and then the output is 0. So this chip is selected. Okay, at that time, this is enabled. Fine. So this is how this is done. Okay, and this you can say this circuit, this entire circuit is called address decoder circuit. So we'll see the further extension of this to our microcontroller where we have 16-bit address bus. Okay, in that case, we'll see that how different ROM and RAM chip are connected and how those different memory chips are enabled. Okay, so this is going to be quite interesting in the next class. So we'll stop here because we have discussed a lot of things. Okay, so thank you everyone.